Hello dearest physics students, welcome back to Rubber Duck Physics. In the last video, we saw how the Michelson-Morley experiment challenged the concept of absolute motion. Today, we will explore the mathematical framework that reconciles the absolute speed of light with the laws of motion, the Lorentz transformations. Let's dive in. The Michelson-Morley experiments showed that light speed remains constant, regardless of the Earth's motion through space. This result was puzzling, because it seemed to contradict the classical idea that velocities should add up, as in Galilean relativity. To resolve this, a new mathematical framework was needed, one that preserved the constancy of the speed of light while reconciling it with the laws of motion. Imagine you are standing still in one reference frame, watching light move at 300,000 kilometers per second. Now imagine someone else in another reference frame moving relative to you, say on a spaceship passing by. Classical physics would suggest that the other observer should measure a different speed for the same beam of light depending on their motion. But the Michelson-Morley experiment proved this isn't the case. Both you and the moving observer measure the same speed of light, something that Galilean transformations couldn't explain. This is where Hendrik Lorentz stepped in. He developed a mathematical transformation that ensured the speed of light remained constant in all reference frames, even for observers moving relative to each other. This transformation was essential for Maxwell's equations of electromagnetism to work universally, no matter the observer's speed. Here is what the Lorentz transformations look like. For position, the equation is x dash equals gamma times bracket x minus v times t. We'll talk about the value of gamma in a moment. For time, the equation is t dash equals gamma times bracket t minus v times x divided by c squared, where c denotes that absolute speed of light in vacuum, almost 3 to the power of 8 meters per second. The gamma factor in both equations is given by gamma equals 1 divided by the square root of 1 minus v squared divided by c squared. Let's take a moment to check how gamma changes with v, the relative velocity between the two observers. When v equals 0, the gamma factor equals 1. This means for two observers not moving relative to each other in the same inertial frame, the Lorentz transformations reduce to the familiar Galilean transformations, where space and time remain unaffected. For speeds less than a tenth of the speed of light, the value stays very close to 1. That's why you cannot observe these effects when you travel at any speed ordinary to you. As v increases, the denominator of gamma gets smaller, so gamma grows larger and larger when v approaches the speed of light, gamma approaches infinity. These transformations ensure that the speed of light remains constant, resolving the paradox posed by the Michelson-Morley experiment. Let's see how these equations work in a practical example. Imagine two observers, one on Earth and one on a spaceship moving past Earth at half the speed of light, or v equals 0.5 c. At the moment the spaceship passes Earth, the clocks in both frames read 0, meaning t equals 0 and t dash equals 0. Now, let's say a space probe crashes into an asteroid 300,000 kilometers away from Earth at t equals 1 second in the Earth's reference frame. We want to calculate the position x dash and the time t dash of the event as measured by the observer on the spaceship. First, calculate gamma. Gamma equals 1 divided by the square root of 1 minus 0.5 squared, which is 1 minus 0.25 or 0.75 below the square root. The value of the gamma factor is approximately 1.15. Now, for the position, x dash equals gamma times x minus v times t. Substitute the values, x dash equals 1.15 times bracket 300,000 minus 0.5 times 300,000 bracket back. Simplify that x dash equals 1.15 times 300,000 minus 150,000. That gives x dash equals 1.15 times 150,000, or approximately 172,500 kilometers. For the time, t dash equals gamma times t minus v times x divided by c squared. Substitute the values. T dash equals 1.15 times 1 minus 0.5 times 300,000 times 300,000 divided by 300,000 squared, which equals 1.15 times 1 minus 0.5. That gives t dash equals 1.15 times 0.5, or approximately 0.575 seconds. So, in the spaceship's reference frame, the event happens at a position of approximately 172,500 kilometers, and the event is measured to occur at approximately 0.575 seconds. This example shows how the Lorentz transformations adjust space and time between two observers moving relative to one another while keeping the laws of physics consistent. You can, of course, rearrange the equations to find the x and t values from the x dash and t dash values. That's also called the reverse Lorentz transformation of position and time. If one observer detects not a single event, but an object moving at velocity u, remember we can't call it v now, in their frame, let's mention it without expanding it further that it's also possible to transform its velocity by the Lorentz transformation to find out what value the other observer will measure. U dash equals this fraction, u minus v divided by 1 minus u times v divided by c squared. The Lorentz transformations replaced the Galilean transformations for scenarios involving high speeds. While Lorentz himself viewed his equations as a way to make the math work, Einstein later revealed that they reflect the true nature of the universe. Time and space are relative, not absolute. In the next video, we'll explore Einstein's two postulates of special relativity and how they provide the foundation for this revolutionary view of the universe. Before we wrap up, let's quickly summarize what we have learned. The Michelson-Morley experiments showed that the speed of light is constant, independent of the motion of the source or the observer. The Lorentz transformations resolved the paradox by showing how space and time adjust to preserve the constancy of light speed. They replaced the Galilean transformations and paved the way for Einstein's theory of special relativity. Before we go, let me mention that I also tutor students in physics and maths at the high school level. If you are studying IBDP physics, but also if A-level physics or maths, AP physics or similar subjects, and you would like extra support, I'm here to offer personalized help individually or in small groups. You can find my email address in the channel data of the Rewrote Physics YouTube channel. View it in a browser on a computer. At least at the time of publishing this video, the YouTube app doesn't display it. Feel free to reach out and let's find out together if I can help you. Thank you for watching Rewrote Physics. See you next time.